10 raised to 3, and it will give you an idea. So anytime you look at that number, you will get an idea about how many times a bigger a picture that you are looking at. And since we don't always use meters, when we go to 1000 meters, we say a kilometer, and when we go to 10,000 million kilometers and all that. So this number below will tell you what are the typical units used when we are on that size scale. So the first number will give you how many times bigger a picture that you are looking at, and the second number will tell you what are the typical units we use when we talk about that size scale. So this picture is 1 meter by 1 meter. A typical human being is about 1.8 meters or so, so you can imagine drawing a cube 1 meter by 1 meter around you. And the first thing that you notice is that that 1 meter cube is your personal space. We all like to own this meter cube. So we put perfumes on our body because so that 1 meter cube smells nice. We don't like mosquitoes within a meter cube. If there is fire within a meter cube from us. So that 1 meter is something we all like to own, we all like to possess, and typically, even if I don't know who you all are, I can typically tell you who is friends with who, because we don't even like strangers within a meter of us. So unless it's a public transport or something bad like, you would sit next to that 1 meter space would be occupied by somebody you know or somebody you are friendly with. 1 meter cube is my personal private space which I own, which I try to control to the extent possible. I go air conditioning, I go perfumes, etc. because I like to own this 1 meter cube. You go to 10 meters, and roughly 10 meters is the width of this building, and then things start getting scattered in the sense that my personal control no longer remains. At 10 meters from me, various things can be happening, various things are happening, and therefore at 10 meters, my personal control or my personal ability to handle goes away. Not only that, if I want to talk to somebody 10 meters away from me, I need to use an amplifier system because my voice can't be heard. Of the 5 senses that I have, touch, taste and smell, touch and taste are definitely gone. Smell is useful only if the smell is really, really small. In most cases, I can't even smell at 10 meters. I can hear at 10 meters provided the sound is loud, and I can just about see if there is no wall. So essentially out of my 5 senses, one works very well, which is the sight, second one, hearing is borderline, and the other 3 senses are essentially not even useful. So by 10 meters, already I am talking now about sizes which are so large that is beyond my personal confine. You go to 100 meters, which is roughly the distance from here to the main road, and then I have personally completely lost track of everything. Right now there might be a big fighting going on at the other end of the road, and I won't even know. Just the second slide from where I started, at 100 meters, now things are way beyond me. Not only that, if I'm sitting here and if I have some friends come who want to have something, and if the restaurant is 100 meters away, chances are that I'll phone up and ask them to deliver it to me because I don't want to walk 100 meters. 100 meters is an irritating distance. In a city like Hyderabad, for example, if you have buses, the buses will have a stop every 100 meters because we don't like to walk 100 meters. At 100 meters, we are already talking of distances which are irritating. You go to a kilometer, now the distances are so large that we don't even think of walking over a kilometer distance. For a kilometer distance, you will essentially lose track of a lot of things, in the sense that even if you are living in the same place all your life, you will not know 99% of what happens within a kilometer square from you. Just about 100 meters, you have a good idea. Within a kilometer, you will probably not get lost. You can keep a map of a 1 square kilometer around without difficulty. You will know all the important shops within a kilometer square of you. But honestly, you won't know most of what happens within a kilometer square. At kilometer square, you have already lost track of what you can keep track of. At 4th slide, at 100 meters, I said it was irritatingly long. By a kilometer, I have now lost track of what I can do. You go to 10 kilometers, and in fact, you reach another limit. At 10 kilometers by 10 kilometers, it is 100 square kilometers. No city in the world is more than 100 square kilometers. If it becomes more than 100 square kilometers, it is divided into a smaller city. And the reason is that for whatever you may claim about your state and your nation and all that, your daily requirements are met by your municipal corporation. So your water supply, your security, your drainage, everything is looked after by your municipal corporation. And they'll tell you that if the city is more than 100 square kilometers, it is so large that no single municipal corporation can manage it, and therefore it has to be divided between amongst smaller municipalities. And that is true anywhere in the world. It's not just a question of India, but anywhere in the world, no city exceeds 100 square kilometers because it is simply too large for us to manage. So at 1 square kilometer, I said I have lost track of what is happening. At 100 square kilometers, my municipal corporation has now found the thing unwieldy. And if you go to 100 kilometers by 100 kilometers, you essentially end up with distances which are so large that if you are in a particular city, and if somebody comes to you from a city that is 100 kilometers away, you will know in 10 minutes flat that that person is not from your city. Because even if you speak the same language, their attitude will change, their behavior will change, their responses will change, their vocabulary will change. Essentially, culture changes over 100 kilometers. Over 100 kilometers, the populations are not the same. Their attitudes, their behaviors, you can easily tell that this person is from a place more than 100 kilometers from you. So at 1 kilometer, I lose track. At 10 kilometers, I lose my ability to organize. And at 100 kilometers, we actually have disjoint cultures. Even if you have same language and same other education and all that, your vocabulary and your perception will definitely have subtle changes, which are easy to see. At 100 kilometers, we have reached there, and this is just the sixth slide from where I started. You go to the 7th slide, and you got to come 10 raised to 5 meters, 10 raised to 6 meters or 1,000 kilometers. On this size scale, no city matters. All our human population that coming from Mumbai with a city of 15 million, we don't even merit a single point on this graph. Human beings are completely irrelevant on the size scale of 10 raised to 6 meters. The only thing that matters is that water has a higher specific heat than land does. So for the same amount of light that falls from the sun, this area will not get hot very quickly, this area gets hot very quickly, and therefore the air around it is low density, and the air will flow from the sea to the land, bringing moisture with it, and wherever you have lots of moisture, you will have life, and wherever the moisture is less, like in runoff Kutch over here, you get dry places where you can see the barren land, and we call it a desert. On a 1,000 kilometers size scale, the only thing that matters is the fact that the specific heat between water and land is different, so water gets hot very quickly, and that is all that is the dynamic. At 100 kilometers, already at 10 raised to 6 meters, we have lost we are completely irrelevant to the story of what is happening to the universe. You go an order of magnitude up, and now you can see the Earth. The Earth's diameter is about 12,000 kilometers, so you can't see the whole of the Earth, but essentially you can see most of the Earth. And this is one of the most beautiful and strangest objects in the universe. We have looked for planets like this around thousands of stars in our neighborhood, and we know what, by now 3,000-4,000 planets around an equal number of stars, but we have seen nothing like this. Look at this piece of rock and take it 10% closer to the sun than it is, and it will be so hot that life on Earth will not be possible. Take it 10% further away from the sun, and it will be so cold that life on Earth will not be possible. Make it 10% smaller than what it is, and the entire atmosphere will evaporate away, and life on Earth will not be possible. Make it 10% bigger, and our own weight on Earth will be so much that we will find it difficult to walk. This piece of rock has a tilt of 23.5 degrees. You change that, and you make it vertical, and essentially you will have no seasons, and life on Earth, there will be no water on land mass, and therefore life on land will not be possible. This piece of rock, essentially as it goes around the sun seems to go north and south. And if you think about it, the landmass of India is a very peculiar geography. The monsoon in India, on which we all survive, has nothing to do either with the Arabian Sea or the Bay of Bengal, because the monsoon in India is decided in the southern Indian Ocean. In fact, right now, over the next 2 months, in December, January, February, we will know the monsoon of India. Monsoon of India will have been decided in the next 2 months, because right now when we have winter, they have summer. And in the summer months, massive amount of water is being evaporated in the southern Indian Ocean. And as April, May comes, that moisture moves upwards. And that is why the weather bureau will tell you in April or May whether we are going to have a good monsoon or not. You can see how much moisture has moved in. By April, May or June, the land becomes so hot that the differential pressures between cold and warm air become so much that all that moisture gets pushed into the Indian subcontinent, and we have our monsoon. Monsoon in India, therefore, is entirely dependent on what happens over here. So even if you don't like Australians, at least thank them for being much further away. Because if Australia was here, there will be no evaporation in January, February, there will be no monsoon in June, July, and you will be as barren as Northern Africa. So Australia, by being 2,000 kilometers further east, has actually made life on Earth, not only in India, but all the way from Saudi Arabia to here. Everybody depends on monsoon, simply because of the fact that there is more land mass on the north, more sea mass in the south, and water can take in a lot of heat, but once it gets warm, it's not easy to condense it off, and therefore it remains the moisture, and that moisture eventually comes out as monsoon. You go in order of magnitude up, and the first thing you notice is that you don't see anything else. Take the box into which you could fit the Earth, make it 10 times bigger on each side, or 1,000 times bigger in volume, and you don't see anything else. The moon at 300,000 kilometers is still a factor of 3 further away from the Earth. Essentially, the box is empty. You go in order of magnitude up, and now you can see the orbit of the moon. The moon goes around the Earth once in 27.5 days, and the Earth takes about a couple of months to go across this. But on 10 raised to 7, 10 raised to 9 meter size scale, at 1,000,000 kilometers, it's a fairly lonely, empty space. You go in order of magnitude up, and again you see nothing new. The Earth now is 1,000 the size of this box. So essentially it's like saying that if I take a box which is 1 meter by 1 meter by 1 meter, and put a speck of dust which is 1 millimeter in size, the box is full. That's all that is there. 1 millimeter size, the piece of dust in a meter size box, and that is all that exists on the size scale of 10 raised to 10 meters. You go in order of magnitude up, and now you can see a bit of orbit of Venus, orbit of Earth, and very little of the orbit of Mars. And again, if you are doing your density calculations, the density numbers become absurd. The average matter density becomes horrendously small, but you can see a bit of, because Venus just adds twice the moon. Venus has the same mass as the Earth, so you increase the mass of the box by a factor of 2.5, but you increase the volume by a factor of 1,000. So essential things become emptier and emptier. You go in order of magnitude up, and now you can see the solar system. You see Mercury, Sun, Mercury, Venus, Earth, Mars, and bit of orbit of Jupiter. Life on Earth arose about 4,500 million years ago, and since then it has been gradually becoming more sophisticated. And the first solution of sophistication was essentially to have dinosaurs, which were bigger and bigger and bigger animals, because every bigger animal could outwit the smaller animal. Until the animals became so big that they became unstable. And a single comet hit 65 million years ago, produced a winter that lasted 3 years and essentially killed all the dinosaurs. 90% of life on Earth disappeared. One single comet is back 65 million years ago. And it was subsequent to that intelligent life forms in charge of this piece of rock. But if you remove Jupiter, Saturn, and if you look at the amount of debris that exists in the solar system, you would expect such collisions to happen once every few thousand years, or few tens of thousands of years. Which means life on Earth would be reset continuously every 10,000 years, in which case there is no question of having intelligent life. But fortunately we have 3 major vacuum cleaners, Jupiter, Saturn, Uranus and Neptune, 4 major vacuum cleaners, who make sure that the number of dust particles that come and hit the Earth is not very high. Without Jupiter, Saturn, Uranus and Neptune, typically you would get a collision every 10,000 years or so. Because of Jupiter, that probability goes down to once in 100 million years or so. So Jupiter, Saturn, Uranus and Neptune are gigantic vacuum cleaners, and they are crucial to the evolution of life on Earth. At 10 raised to 12 meters, you see so you can see the last of the protective shields at about 10 raised to 13 meters. Jupiter, Saturn, Uranus and Neptune, which protect us from all the debris from the space that is coming in. The question to ask is, where is the nearest star? After all, when we do astronomy, we are told about the Earth, the planets, Earth, Moon, planets and stars. And the question is, where is the nearest star? If I take this box if I take this box and make it 10 times bigger, I see nothing else. I make it 100 times bigger and I see nothing else. I make it 1,000 times bigger and I don't see anything else. I need to make the box 10,000 times bigger in each size, 1,000,000,000 times bigger in volume before I can see the nearest star. And that too, the nearest star is not even visible to without a telescope, but essentially you can see Alpha, Beta Centauri, the brightest star in the night sky, Sirius, and a couple of more stars. You have to take the box into which you fitted the solar system, make it 1,000,000,000 times bigger before you see the nearest star. And in fact, the distances are now absurd in the sense that light traveling at 300,000 kilometers per second also takes several years to come and reach us. So if you go out tonight and if you ask me what does Sirius look like today, I really can't give you an answer. Because if you go out and look at it today, you will see it as it would have been on the 3rd of February 2007. Because even light takes 10 years to come. From the sun, light takes 10 minutes to come. From Sirius, the light takes 10 years to come. Even though light travels at 300,000 kilometers per second, which means it can go around the Earth thrice in a matter of second, in a microsecond or so. And yet, the distances now become so astronomical that to look back or to look at larger sizes, you are looking back into the past. You are never going to be able to say what is the situation today. You go in order of magnitude up, and then you can see a lot more stars. But essentially, most of the stars that you see in the night sky are roughly from within this distance. They are about 10 to 18 meters bigger size scale than you and I are used to. And there are 3 spectacular exceptions to that, and we will come to those in a little while. But essentially, most of the stars that you see in the night sky are over there. You go in order of magnitude above what you can see, and you still see nothing spectacularly new. So where is the galaxy? Even to get a glimpse of the galaxy, we need to go in order of magnitude up. At 10 to 20 meters, at 10,000 light years or 3,000 parsecs, forget the parsecs, but 3,000 light years, you now have the Earth in the middle, and the sun is now so small that you can't even draw it, but you get the city light effect. So there's a huge colony of stars on one side, there is a huge colony of stars on the other side, yes.
How do you estimate the distance of the star to the Earth?
What you do is, for example, I'm standing here, and with respect to my vertical, you are about 5 degrees to the right of me. If I measure you again after some time, you are now about 3 degrees left of me. This distance is 2 AU. So if I do measurements in January and June, the Earth has moved twice 2 AU with respect to the Sun, and your distance, the angular change I can measure. So I look at star, measure its location with respect to me in January, look at it, measure in March, and by triangulation I can tell the distance. Most of these distances are measured like that. For longer distances, you have to use what are called standard candles. So for example, if I know what you look like, then if you go farther away, by seeing how faint you have become, I can tell you how far you are. And nature has provided us with some good standard candles, where the star changes its intensity depending on how big it is. And you can use those to determine the distances. And then there are other variants of the same thing. So measuring distances is a very sophisticated job on this size.
Given the fact that depending upon the brightness of the star, you would understand whether it's like faint or less faint, which is one of the factors you take into consideration while calculating.
No, see the thing is that the stars have a variety of sizes. So a star may be fainter because it is intrinsically faint, or it is further away from you. And you need to be able to find the difference between them.
How would you do that? How would you find it?
So I only go by distance, by parallax, what I say. I measure your location in January and June.
So that way you...
That is independent of your absolute intensity.
Won't the parallax work only if that star is stationary?
Yeah, but these by astronomical standards, these stars are stationary. In the sense that typical distances are about 1 second of an arc. Over a period of 100 years, a typical star would move less than 1 arc second in the sky. Because these distances are extreme. So the angular sizes are small. Except the planets, nobody really moves very quickly. Planets are very close. Okay, so you have this if you are astronomy minded, yes.
So why are stars stationary?
Why are stars stationary? They are not stationary.
You said they are not moving.
Yeah, so we don't live long enough.
Okay.
Okay? In 100 times, what happens is, imagine that this star is moving at 100 kilometers per second, which is typically a very fast, or even this whole galaxy which is rotating at 250 kilometers per second. But even at 250 kilometers per second, it must move several arc seconds for its angle distance for me to change. Because the distances are very. This is several tens of light years. So unless you move a light year, this is tens of light years. So unless you move a light year or so, you are not going to look different from me. And to move a light year even at 250 kilometers per second, will still take you 1,000 years. Okay? Moving at 300 kilometers per second, moving 300,000 kilometers is still going to take you 1,000 years. And those kind of speeds don't exist. 1,000 kilometers per second just doesn't exist. So that's why they appear stationary, because we don't live long. Okay, so you have, if you are astronomy minded, this is where the Scorpius arm is, and this is where the Centaurus arm is, and the Earth sits, Sun sits somewhere over here. You go an order of magnitude up, and now you can see the galaxy. By astronomical standards, it's a fairly large sized galaxy, not the largest, and there is a large black hole sitting in the middle, about 1,000,000 times the size of the Sun, and the whole galaxy is rotating at 215 years. How do we take this? This is a cheating. In the sense that what I have done, what astronomers do is to sit and measure the distances to everything. So if I start measuring, I will see that at this distance, I will see her at a certain distance, then there is a 1 meter of empty space, then she is sitting, then there is 2 meters of empty space, and she is sitting, he is sitting. Then I can plot it on the map. And then I get a picture, and then I go around looking what looks similar to that. So this is actually a galaxy that is similar to our galaxy. Okay, so this whole galaxy goes around at 250 kilometers per second, yes.
So how do you know what position you are in on the galaxy?
We are here.
Yeah, and how do we know that?
Okay, what happens is that if you start measuring from here in 360 degrees, okay, you get a region where there is an extremely high density of stars. Not only is there a very high density of stars, there is a region there which is smaller than the size of the solar system, which has mass equivalent to 1,000,000 times the size of the Sun. The reason why I know that it is 1,000,000 times the size of the Sun is because how one body reacts with another body depends on the mass of the body. Okay? So at the center of the galaxy there is a very, very heavy object. It will make everything around it move very fast. And by measuring the speeds of the things that are moving around the center of the galaxy, we know that there is an object that is 1,000,000 times the size of the Sun in the center of the galaxy. And given that this is 1,000,000 times and everything else is much, much smaller, it is safe to assume that this is the center. The second thing is when I measure densities, I get lots of matter here, lots of matter here, lots of matter here, nothing in between and so on. And then I sit and plot it on a graph paper. And then go back and reconstruct. So that's how I know that this is the center of the galaxy. And on that side I see very few stars, on this side I see very many more stars. So if you go to night sky, for example, you can see a beautiful Milky Way galaxy. This is a good time to go, December, January, February. Early morning, you will see a huge patch of fuzziness which consists of millions of stars, and that is because in January, February you are seeing this region of the galaxy. In June, July you will see this part of the night sky. In January, February you will see this part of the night sky. So the center of the galaxy becomes visible to us in November, December, January in early morning skies. By February, March, April it will be essentially late, early night sky and so on. But you can see this Milky Way. So we call our galaxy the Milky Way because it was not seen as a Milky Way path in the sky, and now we know that it's a galaxy. Okay. So if I go an order of magnitude above this, by now I realize that the Earth is not a very important object, and yet Earth has a moon of its own, so there is no reason why a galaxy should not have a moon of its own, and surely we have about half a dozen, about 8 or 10 galaxies that are going around our own galaxy. Each of them is much smaller than our galaxy, so these are the two of the three brightest objects that I talked about. One is called the Large Magellanic Cloud, and the other one is called the Small Magellanic Cloud. Small Magellanic Cloud you can see from India in the southern sky. To see the Large Magellanic Cloud, you need to go to southern hemisphere. But these are the two nearly the farthest of. There is still one object which is much further away, which you can see a little later. But on 1 mega light year, or 10 raised to 22 meters, this is what our universe looks like. You go an order of magnitude up, and then you come to a rather interesting, quiet, stable neighborhood. There are about 30 galaxies that make up the neighborhood in the size scale of 10 raised to 23 meters. We are Milky Way galaxy is in the center, and Andromeda Galaxy is our nearest neighbor. And you can see this without the telescope. This is the farthest object that you will be able to see without a telescope, because it's a galaxy, in fact, slightly bigger than our galaxy. And it also has trillion stars, and the two are in fact headed for a collision sometime in 5 billion years from now. So if you're planning to live that long, you will see a beautiful spectacular event in the night sky, because both the galaxies will be in the sky colliding with each other. You might have a slight problem because the sun will be dead by then, so you will need some more warm clothing, but otherwise you get a spectacular view over here. But otherwise, you have a rather quiet neighborhood. There are about 30 galaxies. None of them are moving fast enough to be able to run away from this cluster. So this little group of 30 are going to remain together for a long time. Yes?
How do I distinguish as a galaxy?
How do I distinguish a galaxy? What I essentially get is in a small field of view. Now this is less than an arc second in size. Okay? And I get thousands of stars within that. So sheerly by photography, I can make out that this is a cluster of stars.
If it's really far, then I will not be able to do it.
You'll be able to see the stars. With a good telescope, you can see the stars. So Andromeda Galaxy, if you look at without the telescope, it is just a fuzz in the sky, and you will need some astronomer to convince you that this might have stopped working. Okay. No, I think it's okay. I can press the button now. So if you look at Andromeda Galaxy without a telescope, it looks like a simple fuzz in the sky. No, I think it's right. Okay, so what happened if you look at, like I said, without a telescope, it looks like a fuzz in the sky, and in fact you need somebody, some astronomer to convince you that that is really a genuine object. You put a telescope to it, even a small telescope to it, and it will immediately break into several bright stars. And you know that there is a whole group of bright stars. In fact, the earliest names of galaxies were called island universes, because there are these islands of stars and nothing in between. So you have these galaxies in between, yes.
So if I look at the image, it seems like these galaxies are all spread in some orientation.
Yes, correct.
But I'm just wondering, how is that the stars will be clustered in these spaces? Like in between, if there is a black space, does it mean there is no star there?
Yeah, there essentially means that there is no star.
There's nothing.
The reason is, okay, it's a good question to ask. Why are there island universes, and why are the stars not uniformly distributed? And the reason is, it carries the signature of the birth of the universe. When the universe was born, the stars that we had were huge, massive amounts of, because the universe was small, there was a lot of material, so you could accumulate a huge amount of material in one place, and you could make massive stars which are typically a few hundred to a few thousand times the size of the sun. The problem with stars is that the bigger they are, the more quickly they need to burn their fuel in order to remain stable. So the bigger the star, the shorter is the lifetime. So these stars that were 1,000 times the size of the sun essentially died out in a matter of few hundred thousand years. When they died in a matter of few 100,000 years, they left behind these gigantic black holes, and those gigantic black holes clustered material around them and formed galaxies. So in each of these galaxies, you will see a black hole which is typically a few million times the size of the sun, which controls the local environment. And that is how we have galaxies in the universe. Yes?
Yeah, does this color represent anything?
The color typically represents what happens is that the smaller the star, the cooler the star. The bigger the star, the hotter the star. And the hotter the star, it is bluer the star. It is in the blue end of the spectrum. A warm star will be in the yellow. Sun is a warm star, so it's in the yellow of it. And the coolest of stars will actually be red in color or infrared in color. So when you see, for example, in a picture, just to go back to the previous picture, what you see here, you can't see probably very well over here, is that this is an entire collection of yellow colored stars. These are all old, young, small, medium-sized stars that have survived. The big stars that existed in this area have died and gone on a long time. On the other hand, if you look at this region carefully, because this galaxy is spinning, okay, it is pushing the material ahead of it in a compression. So you see a lot of young stars being born here. So typically if you look at a galaxy, the center will look yellow and the edges will look blue, because that is where there are lots of young stars which are blue in color. And you can determine the age of all kinds of things by counting the number of blue stars in the galaxy. So yellow essentially means that you're talking about moderate size stars that have sort of outlived all the other stars in their neighborhood. Blue stars are young stars, huge stars, they're not going to live very long, and therefore you know that they were born only recently. Recently in astronomy, by the way, is 100,000 years. Okay? So in that sense of the word recently, but yes, you see, so color differences are very important to stars. Yes?
How do you image something that is behind something? I have a telescope that can only point in one direction.
Yes.
How do I
In principle, I cannot. Okay, in principle, I cannot, and the reason I'm reserving that statement is, I'll come to in a minute. In principle, I cannot see what is behind me. But the probability that something is obstructing something else is relatively small. The objects are rather small in size. Even then, there are obstructions. But then, over the last 20 years or so, we have realized something strange. That we all have lenses, at least I have lenses. Okay? What the lenses do is to bend the light and bring it in. Gravity also works like a lens. And so if you have a heavy object that is in between me and something else that is behind, the light coming from that object behind will actually be bent and brought to me. Light that would have otherwise escaped. So these heavy objects become gravitational lenses. And they are slightly inverted from the optical lenses in the sense that if you look at an optical lens, the center of the optical lens, typically the light goes straight through without any bending. And the further away from the center of the lens you are, the more is the bending. That's how you get your focusing. These lenses are weird. The closer you are to the object, the greater is the bending. And the further away you go, the weaker. So it's an inverse of an ordinary lens, but it's still a lens. And by lensing, you can see objects which are much further away. And typically, how do you know whether these two images that you see are two different objects or the same object being seen twice? And generally, what you do is that you look for something that is changing in one of them that you can measure. But more likely, what you will do is you will ask how many stars of which kind are there in this image and in this image. And if they are nearly identical, and if I can show by simulation that this gravitating object will produce this lens, I would go back and say that two images are the same. Okay. So they are called Einstein's crosses, but typically you see 4 images. So they are called Einstein's cross because it comes from general theory of relativity. But so the only way of seeing an object that is behind something else is if there is a gravitational lens.
How do you get to know which one is behind and which one is in front?
Typically in that cases what happens is that the front one either will be very bright, and the second, the more important feature is that the lensing typically does not produce spot images. It produces curved images based on the curvature of the lens itself. So when you see a curved image, you become paranoid. It's probably gravitational lensing. So look at all these curved images, see how many curved images you get. All of them are assuming that there is a central object, and see if they all coincide to the same point. And then you know that you've got the correct image. But it requires some skills. And it requires some practice more than anything else, to figure out which is a lensed object and which is the real object. Okay? So you have at 10 mega light, and the reason why I'm saying that this is a rather quiet neighborhood is that if you go in order of magnitude up, if you go in order of magnitude up over here, you will know what I mean. So we have a local group of galaxies, 30 galaxies doing nothing in particular, colliding with each other once in a few 100 billion years or so. But there are huge clusters of galaxies around. One galaxy is a trillion stars. Okay, so we are talking about massive numbers. One galaxy is a trillion stars, but you get these huge clusters of galaxies in various parts of the sky. And if you look at them by a bigger picture, the picture looks very strange. There are regions where there are lots of galaxies, and then there are regions where there are no galaxies. And if you think this is a strange picture, this is a picture you see every day in your daily life. If you take a bucket of water and put detergent in it and rinse it, essentially you get the same picture, except of course here in that case this is a form of soap and these empty regions are air. In this case, empty regions are vacuum and the foam is galaxies, thousands of galaxies. And this is the froth from the birth of the universe. How well do you know this froth? We really don't know fully how well it is arisen, but we know that this is the froth of the birth of the universe, which happened 14 billion years ago. This is about 1 billion year size image. 14 billion years ago the universe was born, and so this is the froth from the birth of the universe that you see on 10 raised to 25 meters or 10 raised to 10 light years. You go in order of magnitude up, and now you can see this froth and film structures very clearly, and you can see the whole. So the Earth is sitting over here. From there you measure where do you find a galaxy around various angles, combine and plot it on a graph paper, and this is the image that you get. The universe was born in one big bang 13 billion years ago. Sorry, 13 billion years ago. So this is the largest picture of the universe that I can show you. Because the light that you are getting from over here is roughly the light that left that star when the universe was just born. The universe is about 30% bigger than this, but we can't see the earlier part of it simply because at that time the universe was so dense that no light escaped from there. So there is no light for us to see anymore. This is the farthest light I can see at 10 raised to 24 meters, 26 meters. This is the biggest picture of the universe that I can see. And like I said, as you see further back in space, you see further back in time. So the galaxies that you see at the edge were the galaxies that are just being born at a very early age in the universe, and these are the galaxies that are roughly of our age. That's what the picture looks like when you go to the largest picture of the universe. And like I said, this is the largest picture of the universe that I can show you. Just to revise, yes.
Why does it have such jagged edges?
That is because of observation problems. There is something in front that is obstructing the back view and stuff like that. So for example, here you can't see it. There are squares over here because there's something here that obstructs.
No, I mean the edge of the diagram.
Edge is observation, entirely telescope problem. Okay. Just to revise, when I started, we started with 10 raised to 0 meters. And I said by the time we came to 10 raised to 3 meters, 1 kilometer, I lost track of everything. By the time I came to 100 kilometers, I said cultures now got disconnected. And the universe goes on to 10 raised to 26 meters. Let's see what happens when you go down. Okay? So we come back to 1 meter, which of course makes us feel more relaxed and comfortable because the dimension we understand. But let's see how far we can go down. So you go to 10 centimeters. And 10 centimeters is not a problem. This is the back of a hand, and in English language there is a saying that if you know something very well, you know it like the back of your hand. Because sometime or the other we were getting thoroughly bored and the only thing that we could do was to look at the back of our hand. So we know every hair and every deformity in the back of our hand. Back of the hand is something we all know. 10 centimeters is not a problem. You go to 1 centimeter, and at least if I argue with you about the sweat and the sweat glands and the hair roots and if you have played with the magnifying glass and looked at your skin, at least at 1 centimeter I can convince you that the universe looks like this. You go to 1 millimeter and then the things start becoming messy. Our skin on this size scale is extremely wrinkled, and it doesn't matter which smoothing cosmetics you use, our skin is this wrinkled. And within our skin, something like 250 million germs live within each of us, and irrespective of what kind of soap you use, whether you use Dettol soap or whether you use some other soap, essentially this 250 million population is not changing. It might increase at times and so on, because when you think about it, if you go to and wash your hands with a soap, the soap bubbles are more than a millimeter in size. They essentially skim all this and not even see the depth of this. The germs will simply see some balloon coming up on the top and going away. They are not going to be affected by it. These germs live in a completely, if you think 6 billion human beings on earth is a bad idea, you should look at your skin. Okay? Yeah. With 250 million germs, your skin is completely saturated. And every time you exercise and no. Let's see.
Old one.
Okay. Let me see. So this skin is extremely saturated. So every time you go for a run and every time you have a good time, it will last for a minute. Do the backing there. Okay. So what happens is that this skin at 250 million germs is completely saturated. When you go for a run and sweat a lot, each of these germs now gets a house with a swimming pool. They are very happy and they multiply very quickly because they are unicellular, so they multiply very quickly. And as they multiply very quickly, they produce a characteristic smell which they call your smell. It is not your smell. It just happens that there are so many unique unicellular structures that are lying within your skin that they give you the unique smell. Just to make your horror story worse, their food is the dead skin cells and their water supply is either your sweat or the shower that you take or whatever it is. And they are forever trying to get under your skin. The result is that the average life expectancy of a skin cell is just 20 days because it keeps continuously trying to fight out these germs that are trying to get into your skin. At 1 millimeter, you have a fairly violent environment to look at. And if you think you're being friendly by shaking hands with somebody, you are not. Because every time you shake hands, some germs from your hand are going to that person, some germs from that person are coming to your hand. And there is no place. If everything is all occupied, all flats are occupied. So essentially they have to throw out somebody else. Okay? So every time you shake hand, you are starting one hell of a violent war in the universe. You can't realize it, but honestly, what happens in your skin, you really don't want to see and you really don't want to compare with the world wars. It's much worse than what happens with the world wars because they are one violent. At 1 millimeter, this is what our universe looks like. So every time your class teacher says you go out of the class, you go and stand alone in the classroom, you can challenge your teacher because it is 250 million plus one of you going. You go to 1.1 millimeter and then you'll see how rough your skin is. Yes.
Add to that is just on your skin, right?
Yes.
0.5 into 10 to the power 8.
Yes.
But in our gut,
those, yeah. I think
about 14.
I think somebody has estimated the amount of weight that is our own and the amount of weight that we carry in terms of these germs and stuff.
Our own weight is more, but their numbers are 10 times more than ours.
Yes. But I still like to say that I am looking fat because of the bacteria in my gut, not that I am fat. Okay, so you go an order of magnitude down, and you come to 10 to the minus 3 meters. And then you realize how rough your skin is. Okay? The Earth, the tallest mountain is 8 kilometers, 9 kilometers, 8.8 kilometers. And even if you take from the depth of the seas to the top of the mountains, it will not be more than 24 kilometers. 24 kilometers on a 12,000 kilometer diameter globe. The roughness is less than 0.5%. The Earth has been polished clean for 4.5 billion years using sand, water, heat, whatever nature could find, and it's one of the smoothest objects that we know. If your skin was to be 12,000 kilometers in size, the mountains would be another 12,000 kilometers in size. That is how rough your skin is. And because our skin is so tough, when you run over it, it's like a big tire running over a small pebble. You don't notice it, but that doesn't mean your skin is not rough. And the germs inside your body on your skin will tell you that they hide in these crevices quite comfortably. But that's how rough your skin is. And it doesn't matter which cosmetic cream you use. You go an order of magnitude down, and then you come to a cell. I'm a physicist, so I hate admitting it, but this is one of the most beautiful objects in the universe. Okay? It's unbelievably fantastic in the sense that this is about 0.01 millimeter in size or 10 microns in size, but there are capillaries in my body which are smaller than that. Now I am about 2 meters tall, and if I have to go through a tunnel which is 1 meter tall, I'll bend down, crawl and go. But these white blood cells also therefore need to crawl. But there's an additional problem to it. Suppose if this is a white blood cell, then that white blood cell has to fight infection. And the only way it can fight infection is that each of these cells has a skin wrinkle which is an exact negative replica of the infection it is supposed to fight. So when I was a young kid, and much to my irritation, my doctor gave me the BCG vaccine. One of the things he ensured was that for the rest of my life, I am producing white blood cell whose skin is exact negative replica of the polio virus. Then every time the polio virus entered my body, this white blood cell would connect to it. As it is connected, it would know that this infection has come, send out massive amount of acid to destroy that virus and itself. And if too many of these white blood cells of polio kind died, they would send an SOS to my bone marrow so that the greater number of white blood cells to fight that infection would be produced, and that is how they work. So their entire information is on their skin. Now if you deform them and ask them to go through a cubicle which is smaller than themselves, you are actually causing serious harm, because you have two contradictory requirements. One is that it should be completely rigid, and the second is that it should be completely flexible. And the way nature solves this problem is that she does not fill this with water, but she fills this with jelly. And the advantage of jelly is that if you put pressure on it, the jelly will deform, but the moment you take away the pressure, it restores itself. So fine, you fill it with jelly and you have that cell. The problem with jelly, as with this microphone, okay, this is working, otherwise I'll use that. Okay, the problem with jelly is custard. In the sense that once you have made jelly, you can never ever get anything inside the jelly without breaking the jelly. And the reason why that is important, is that within this jelly is the nucleus of the cell and a whole bunch of chemistry that is happening there, which means it requires energy and it requires garbage to be removed from there. So you need to go inside this jelly and come out of this jelly, and that is not easy. And the way the cell will solve your problem, is precisely the same way in which the city of Hyderabad solves the problem, which is to run railway systems within this. So there are X-shaped cells that are sitting at the top of the cell, and then you put a nutrient on top of it, or nutrient or garbage, whatever it is supposed to do. That top of the X gets bent, and the bottom of the X then starts moving. But it cannot move at random, so there are railway tracks laid out, and the X-shaped molecules goes exactly along that path and goes wherever it has to go. You are talking about railway tracks within a trillion cells in your body on the size scale of 10 microns, that work every day of your life for you and me to survive. Okay? That is why, much as I dislike it, I must confess, it is a beautiful object. Take this, this was a nerve cell, for example. At one end of it, you change slight amount of potential content, and the entire electrostatic potential signal gets transferred to the other end of the nerve down the line all the way to the body. And that sounds very simple, except that you have to think about something else. The velocity of sound is 300 meters per second in this normal air, which means the air has half a meter distance to travel from my lung to my mouth, which means I have about 10 microseconds in which I must speak, or 1 millisecond in which I must speak. Within that 1 millisecond, my brain must decide what I want to speak, send the signal down to my lungs saying my lungs should release the air, which should go through the voice box, and as it comes out of the voice box, my throat, my tongue, my tip of my lips and my mouth must all move in a perfect synchrony based on what I was taught 50 years ago by my school teacher, so that the word that comes out has a meaning. And all that my brain can do in a matter of few milliseconds, because this cell works so beautifully. They work in parallel, so the entire instruction manual is sent down simultaneously to everywhere. But even then, within a millisecond, this cell can manage to make me speak as per the knowledge I acquired later, vocabulary that I acquired later, but the pronunciation that my school teacher gave me 50 years ago. That is how complicated this system can be, and therefore, despite being a physicist, I can't be very dishonest. You go an order of magnitude down, and you see the skin of a cell, which essentially does not look very attractive until you go an order of magnitude further down. And then you realize that the skin of a cell is essentially a molecule, gigantic collection of molecules which are connected to each other, and because these are all chemical reactions, you can cheat with them. So for example, this molecule has a liking for this molecule. So if I bring another one, when this one prefers to connect to this one, it will open up and connect here. Now normally these holes that you see in the skin are so small that not even water will pass out. So for all practical purposes it is rigid. But if I have another cell over here, a chemical over here, this cell, this chemical bond can break, another one can open, and therefore I have a huge hole over here where I can stuff in whatever I want to stuff into the cell, remove whatever I want to remove from the cell, and when I remove this molecule off, the gate will shut. Essentially, you have molecular keys on the size scale of 10 raised to minus 7 meters working in whatever trillion cells that you have in your body, and if you're going to live for 100 years, it has to happen for 100 years in each of them for you and me to survive. Objects 10 raised to minus 7 meters need to be manipulated and played with in order for life to survive. That is how complicated our life is. You go an order of magnitude down, and then you see the instruction manual of life. Okay? Instruction of manual of life has made its life very miserable. Because I speak to you in the English language which has 36 letters, and so a single letter word also makes sense, and so on and so on. The instruction manual of life is written only in 4 letters. 2 of those letters must combine in a specific manner. So essentially you have a binary language manual. And when you have a binary language manual, things become very tricky because every word must be very large in order for it to be unique. And the way the instruction manual is written is that it is like a ladder. And there are 2 big legs of the ladder, but the steps of the ladder is where the information is. The distance between the steps of the ladder carries all the information that it has to. So for example, if I have to read a particular kind of instruction, I go and open that part of the ladder, I fold the 2 legs and the steps become open, and the interspacing of the steps is such that only a particular kind of molecule will be able to replicate itself vertically. So you call it whatever, messenger RNA, whatever you want to call it, essentially we'll make a replica only of the style that fits that stepping of the ladder. You remove it out and you use that as an instruction. Fold back your ladder, fold it up again and put it away. But that means that the instruction manual of life is so long that you can't keep the ladder open all the time. So what nature does is gives it a single twist, which looks like a twisted ladder, and then forces a second twist on it so that the whole thing becomes compact. But minor changes in the steps of this ladder can change the way your life works. So for example, there are steps that decided what the color of my eyes should be. If that steps had been slightly different when I was born, then I would have a different kind of eyes, and so on and so forth. This has complete information about who you are. It tells you how fat you are likely to be, how many bones you have, what is the shape of your bones, how many hair you have, where are they growing, how long will they be, whether you are susceptible to alcohol, whether you are susceptible to cancer in some cases. All that information it has. If you sit under a train and break your leg, it won't know. It will still think you have 2 legs. But apart from that, everything that you are born with, this has. And like all good libraries, there are some sections of this library which are once in a lifetime read. So they're reference sections. They were opened when I was in my mother's womb. That's how I have 4 limbs and so on and so forth. So even every cell in my body, including the ones in the nail, know what my legs look like. I cannot open that part of the library anymore. It's closed and gone. On the other hand, there's a part of the instruction which decides which enzyme should be produced in my stomach for me to digest food, and that works very fine 3 times a day. Thank you very much. There's no problem with it. But this is how complicated your instruction manual of life is, and that is how it works at 10⁻⁻8 meters. You go an order of magnitude down, and now you will see what I mean by that ladder. These 2 are the legs of the ladder which go straight up, and the distance between the 2 steps is what decides what instruction is written over there. At 10⁻⁹ meters, this is what the universe looks like. And to all my chemistry, and I think I'm taking a bad risk here, I like to tell them that the entire subject of chemistry is the study of the universe on this size scale. You go an order of magnitude up and you go to biology, you go an order of magnitude down and you come back to physics. So all you chemists are looking at the universe only on the 10⁻⁹ meter size scale. It so happens that the masses of atoms and the electrostatic forces are arranged in such a way that this is a field that requires a separate study on its own. But that's apart. The entire field of chemistry is the study of universe on 1 out of the 42 orders of magnitude that I will show you. You go an order of magnitude down, and this is what I mean, that you return to physics. If I was an honest man, this picture would be completely black. Because as you will see, the nucleus is much smaller than this. Electron is even smaller than the nucleus, and therefore nothing would be visible on this size scale. All that I'm saying is that if I put the nucleus in the center of this picture, somewhere around here you will find an electron. So I say that the size of the atom is 10⁻⁻10 meters or 1 angstrom. But essentially, this picture will be empty with the nucleus in the middle. And how small is the nucleus? You go an order of magnitude down and you see nothing. You go 10 times down and you see nothing. You go 100 times down and you get a feel, and honestly you have to go 1,000 times smaller in order to see the nucleus. The nucleus is 1 billionth the volume of your atom. That is how small that is, and that is how you have that famous Feynman statement that there is a lot of empty space at the lower size scale, because the nucleus only takes billionth of it. What it means is, in real terms, is that if you take a house yes, we can see the word see, yeah, exactly. So the word see is a complicated one. The question is, can I see this? Okay. In practice, the reason why I know this exists is this, that I can take a foil of material, okay, a thin foil of material, as thin as I can make it, and then I throw a huge amount of charged particles. 99.999% of that will pass straight through with nothing, but 0.0001% will actually be deflected back. Which means that only in about 1%, about 1/10,000th of it, there are some heavy, very heavy objects, and the rest of the space is empty. And then I go back and calculate and I get this. By inference only. Yes, by inference only that you come to the atom. Then there have been other tests to check whether that inference is correct or not. But the first idea comes from there. Okay, so you have this nucleus. And if you think there are a great variety of them, there are not. If you worry about, if you ignore the isotopes, there are only 85 different kinds of nuclei on the size scale of 10 raised to minus 14 meters that really decide the entire variety of the universe. Out of those 85, beyond lead everything is radioactive, you don't bother, it's 85. But essentially beyond 26, nothing is really being made in large quantities, everything is in minuscule quantities. Only 26 different nuclei on the size scale of 10 raised to minus 14 meters decide the entire variety of universe all the way up to 10 raised to 24 meters, 26 meters. Okay? There are just 26 of them that matter. And you go an order of magnitude down, and then you come to the consists of the nucleus. We know that it consists of 3 quarks which are mixed in a particular manner, and they are bound so tightly that you cannot get them to be free. Then they'll forever remain bound inside that. So this is the smallest picture of the universe that I can show you. The question is there something smaller than that? There almost certainly is. Can I see it? No. Can I guess what it is? I have no clue. Okay, as far as we have seen the quarks themselves seem to be fairly solid and point-like. But they cannot be the final objects in the universe, because the other laws of physics tell us that the smallest objects in the universe should be another 15 orders of magnitude smaller. But we don't have the technology to make out what is going on. So just to come back, let me revise what I have been saying. Okay? Human beings are 1 meter in size. Okay? 10 raised to 3 meters is a mountain, 10 raised to 8 meters is the moon, 10 raised to 13 meters is the solar system, 10 raised to 18 meters is the galaxy, and the largest structures in the universe are 10 raised to 28 meters. On the smaller size scale, 10 raised to minus 7 meters is the DNA, 10 raised to minus 12 meters is the atom, 10 raised to minus 7 meters is 17 meters is the smallest object I told you, and theory tells us that the smallest objects in the universe must be 10 raised to minus 32 meters, the Planck length essentially. This part of the universe is entirely governed by electromagnetism. This part of the universe is governed by gravity. This part of the universe is governed by nuclear forces. But we have no idea what governs the biggest and the smallest in the universe. We have a great dream called the Grand Unified Theory, in the hope that someday we will understand what is happening here, because at the end of the day, you know, the universe was born in a Big Bang. So there is a snake over here whose head, which is the biggest object, is actually completely determined by the tail, which is a minuscule object. It's a snake that is connected to head to tail, but we have no clue what this connection looks like. So there are people who study this end of it trying to make out what happens here, and vice versa. Yes?
Why should they be connected?
A priori they should not be connected. We know they are connected because in the end the universe was born in a big bang. When the universe started, it was 10 raised to minus 32 meters in size, and every piece of the universe, every bit of energy, every bit of atom, everything was confined within the 10 raised to minus 32 meters. So that connectivity and the perturbation that caused by that connectivity would show up today. Yes?
How do we know it was?
How do we know? We have an interesting arithmetic. If I stand here and start observing, I get a very strange thing. Somebody who is 1 meter away from me is moving at 1 meter per second. Somebody who is 5 meters from me is moving at 5 meters per second. Somebody who is at 10 meters from me is moving at 10 meters per second. And the obvious question to ask, what was the situation was second ago? And it turns out everybody was at the same place at the same time. In the sense of the universe, that 1 second is 13.7 billion years, but you still get the same observation. That everything was at the same place at the same time. The more interesting point is, where was that point? And it turns out that that point was everywhere. Because the universe had no space and no time. So the universe Big Bang happened where I am standing, the universe Big Bang happened where you are standing, the Big Bang happened where the Andromeda Galaxy is standing, because everybody was at the same place at the same time. But we know it purely from observation. Pure theoreticians would never have predicted Big Bang. Their favorite theory is steady state. The reason why Big Bang works is because observations tell you that steady state is not true. Okay, so that is what we have. So this part of the universe is governed essentially by low density plasma. You can't see it. The word here is plasma. Essentially, this part of the universe is governed by low density plasma. This part of the universe is governed by metals. You cannot make a mountain out of silicon because it will break under its own weight. To make anything on this size scale, you need metals. On the other hand, to do anything on this size scale, you need semiconductors. Carbon is a semiconductor, the very source of life. Silicon is a semiconductor, and so on. because in semiconductors you have an advantage, you can make minor changes in the current, electrical potentials, and you can make it do all kinds of funny things, which you cannot make a metal do, because metal will short out. So semiconductors are the ruling object of the universe on this size scale. This part of the universe is governed by the nuclear forces, but we have no idea what governs the universe on the largest and the smallest size scale. Another way of looking at this is to say that this is the subject that we call astronomy and astrophysics. This is the subject that we call geology. This is the subject that we call biology, and even if you want to let chemists do a bit of biology and a bit of physics, you would fit into a few no more than this. Essentially, I cannot but wrap it in. The whole thing essentially is physics and mathematics specialized to that specific size scale. Okay, so that's what we have on the size scale of the universe. I can do the whole thing on time scale of the universe, except that she will kill me if I was to take another hour. So I'll try and finish as quickly. The universe was born 13.7 billion years ago. It went into a big bang from which stars started forming. First generation stars were born, which didn't last very long. Then second generation stars were born, they didn't do very good either. And the sun is a third generation star. And the sun has enough and has a correct environment and a correct planet where life was born about 3 billion years ago. So this is the 4.5 billion year history of life, and I can't do it faster than that. But I can do powers of 10, which is fun. Okay? So 10 raised to 0 is 1 second. If you go and shine a torch at the moon, the light will take about 1 second to reach the moon. If you take 10 raised to minus 2 seconds, that is how often your television screen is refreshed. 10 raised to minus 5 seconds is how long a megahertz signal, how long my voice remains on your ear. You only have 10 raised to minus 5 seconds to understand what I'm saying. And well, I'm supposed to talk slowly, but still the signal would have remained on your ear for 10 raised to minus 5 seconds. 10 raised to minus 10 seconds is how often air molecules collide and so on. And the smallest signal, the fastest signal that we have seen is 10 raised to minus 15 seconds, or femtoseconds or so. And we are doing better than that. On the higher side, it is more fun because 10 raised to 4 seconds, for example, is the time you would spend in a movie theater. 10 raised to 5 seconds is about a day. 10 raised to 8 seconds is 3 years. The typical lifetime of the longest living being tortoise is about 10 raised to 10 seconds. 10 raised to 12 seconds is how often human civilization has been around. And light takes about 10 raised to 14 seconds to cross the galaxy. And the universe has been around for 5 into 10 raised to 17 seconds. A more interesting way of looking at it is this. Let us assume that the entire age of the universe is 1 calendar year. So the universe was born on 1st January 0 hour 0 minute 0 second, and today is 31st December 23 hours 59 minutes 59 seconds going to the 60th second. And see how the arithmetic works. Okay? If you do that, oh God, you can't see. So the universe was born on January 1 at 0 hour 0 minute 0 second, and your clock starts there. It took the universe, it says February over here, the universe took 1 month, 1.5 months in fact, just to realize that it is born. The first stars don't even get born until February. Just the idea that it is born to look around and see what is happening at sufficiently low density so that the things can be settled takes away a month of this calendar time. The solar system does not even get born till August. So January, February, March, April, May, June and July are gone before the solar system comes into being in late August. That is 4,500 million years. The first life forms on Earth arrive in September, and I am born in September, so I like this name. But essentially, the first life forms on Earth come about in September. Dinosaurs that ruled the Earth were born in early December and lasted for a fortnight in this calendar year. Okay, so the 500 million years for which the dinosaurs ruled the Earth happens to be a fortnight on this 1 year calendar year size scale.
And Mayank, the rocks of Hyderabad are there in September.
Yes, the rocks of Hyderabad in September. Yes. So the solar system, well, they would be as old as August, in principle. The Earth gets born in August.
Yeah, these rocks which we see,
We went through that second volcanization. September also. But the more interesting thing numbers are these. So dinosaurs come in early December and die out in a fortnight. That's all that they lived for. Okay, for all the noise that they made. Homo sapiens arrive on December 31st, 22 hours 24 minutes. So 1 million years of life for which Homo sapiens have been around happens to be 1.5 hours on the time scale of the universe. 1.5 hours out of 1 year. The first human civilization, and if you want to say it around 10,000 years ago, happens on December 31st, 23 hours, 55 minutes. We have been around as a civilization for 5 minutes out of 1 year lifetime of the universe. And just to make me feel miserable, I was born 0.2 seconds ago, and if I live for 0.3 seconds, I will beat the average life expectancy of a human, of an Indian. 0.1 seconds is 25 years, 0.7, 0.3 would be 75 years. So essentially, it's worth remembering, it's not there, okay? That neither on the size scale of this universe nor on the time scale of the universe has been really very important. You should remember that. Thank you very much.
Questions? He's open for questions now.
We have to give out the LCD. Apart from that, we can talk as much as we want.
So if you have any questions, you're free to ask. I think we had quite a few viewers today.
Stars can collapse into the supermassive black hole.
Yes, yes. Okay, the question is, what is this black hole problem? Okay, the black holes are this. Imagine, the escape, if you want to send a rocket into space, the escape velocity is 11 kilometers per second. If I throw something at 11 kilometers per second from the Earth, it will escape into space. From the Sun, it is 400 kilometers per second. Now, I can imagine an object where the escape velocity is more than 300,000 kilometers per second, which means not even light will escape from that object. So essentially, you can't see that object, and by definition, you would call it a black hole. The more interesting story is how do these black holes come into being? Okay? You can imagine if you start with a cloud in the universe which is hanging around doing nothing particular, put some sand pieces on that, they'll start coagulating other sand pieces and you'll start getting clusters. Now, if the cloud is not very large or very efficient, you get a cluster which is like the Earth, where the crust is strong enough to withstand the pressure of the atmosphere and nothing in particular happens on a sphere like that. You increase the Earth's atmosphere by a factor of 100 and the atmospheric pressure will be so much that the the crust of the Earth will collapse and you'll have one deep object, which is what Jupiter is. So in Jupiter, if you try to go inside Jupiter, you will never be able to walk on Jupiter because there is no hard surface. All that has been crushed, but you will be crushed from the pressures on all sides and essentially disappear without ever walking on Jupiter. So you have Jupiter-like objects where internal heat is still being created by the pressure, and that gives you a stable environment. The heat is trying to prevent material from coming outside, from falling inside, and the outer material is trying to fall inside. If you increase Jupiter by a factor of 10, then the pressure inside becomes so much that essentially nuclear events start. So hydrogen and hydrogen will start merging, producing helium, and that produces so much of heat that it prevents outer material from falling inside, which is what happens to Sun. Now, but that is not going to be a permanent solution. In the sense that at some stage Sun is going to run out of hydrogen. When Sun runs out of hydrogen, there will be additional pressure to the center. That additional pressure to the center will now make helium start burning to produce carbon and so on, and it will keep on going until you come to iron. You can't produce material beyond iron because the way nuclear physics works, that beyond iron, if you try to make a heavier element, it does not produce heat anymore. It absorbs heat. So essentially, nuclear reaction in stars end at iron, which is why you don't have too many trans-iron elements, but essentially nuclear reactions stop. At that time, what happens is that we have a core in the center, which is very heavy now. It is essentially iron at extremely high pressures and very hot, and the outer metal that is falling inside. The result is that the whole thing collapses into a kind of cycle pump explosion, where most of the material goes outside, and the inner core in turn gets pressured so much by the core that you end up with an object which is extremely dense. If you start with a small star like the Sun, nothing much is going to happen. You will get a huge, heavy rock, which will initially be white in color because it will be hot, and by Newton's law of cooling, it will cool down and it will become a black box with nothing of great interest. But if you take a star that is more than 3 times the size of the Sun, the kickback of the explosion is so much that the inner core will look like a nucleus of an element. So it will have Z of some hundreds of trillions or whatever you have to call it, but it will be one gigantic nucleus spinning very fast, and we call it a neutron star or pulsar or whatever you want to call it. If I start with a star that is 5 times bigger than the Sun, then the back pressure at the end of the life is so severe that you end up with an object that is so compact that within its radius, even light will not escape. So the black holes are formed like that. Now there are two ways of doing that. One is to take an individual star which is fat and make it die so that you get a black hole. Or you can take two reasonably heavy objects, bang them together, create a new object which is heavy enough and do that. So if you bang 2 neutron stars, you'll get a pulsar, black hole basically. So there are 2 or 3 ways of doing that. Yes?
star is dead, whether we can study further that? No.
Whether when the star is dead, the star death is one of the most spectacular events in the universe. It will emit, within that matter of a few days, it will emit more than 1 trillion times the energy it used to emit as a quiet object. Okay? So when the star dies, it is spectacular. What remains behind also remains hot, and therefore it can be studied for a long time. The more interesting thing is that when the star explodes, the material that goes out now starts reacting with the material that was around, and that reactions take hundreds of thousands of years, in fact millions of years to settle down. So if a star has died, in the neighborhood of that, I will see the expanding explosion from the star interacting with the interstellar medium, and that I can study for hundreds of millions of years. The oldest supernova, they are called, the explosion is called a supernova. Nova is a new star, supernova is a gigantic new star seen in the night sky. And the remnant of that supernova, even though I can't see the core very easily, I can see this expanding force for hundreds of millions of years. If you are lucky, you can see the core in some cases.
Without light, with the energy we can produce.
Yeah, so it will be typically visible in X-rays, and it will be visible in infrared light. If you are lucky, it will be visible in optical light.
Suppose the intensity of light is reducing, whether
Yes.
we know that the star is going to dead or it is far away from the...
Well, we can predict when a star is going to die. So one of the most beautiful stars in the night sky is a star called Betelgeuse. If you know Orion constellation, it is one of the 4 arms of the Orion constellation. That star has more or less run out of its, must have run out of its nuclear fuel from what we can see what's happening on the surface. And one of these days it is going to explode. Except that astronomy being astronomy, one of these days is over the next 10,000 years. Okay? So we don't know where, but over the next few thousand years, Betelgeuse is going. We can see that. Earth has also passed through the supernova shock fronts of some of these exploded stars on the timescales of 2 to 10 million years. So we have had these shock fronts passing through the Earth about 2 million years. The most recent one is about 2.5 million years ago. Some of them are 10 million years and so on. So all those things we have seen. We have seen dead stars. We have seen material from dead star passing through us. We have seen material from the dead star exploding the star.
How do you differentiate whether it is going to dead or it is going away from the path?
Okay, what I
Distance.
can do is I can look at the light from the star. And if I'm good enough, I can not only look at the light that is coming, I can tell you the light is coming from which set of elements. Based on that, I can tell you how old the star is. And based on that, I can get estimate for you the age of the star. And that age of the star will tell me that this star is about to die. And about to, of course, in astronomical sense, but about to die. Dead stars, I can see the remnants of the
If
dead
the distance is high also,
so my efficiency will go down the farther I go. So for the farthest galaxy that we see in the early, it's very rare to see a supernova. For galaxies around us, we typically see one explosion per galaxy per 50 years. So Milky Way's last galaxy explosion must have been, well, it wasn't very far away, the famous supernova remnants. That's it. 1987 is SMC, but anyway, within our galaxy also there have been 3 or 4. Within the human span of 2000 years. Typically, there is an explosion about once every 50 years. Yeah, you had a question.
Yeah, so when you're talking about explosions in the stars, how much time what are the time scales on which these explosions happen?
Okay, the time scales are a very peculiar thing. So a star, let us assume the sun-like star. The sun, when it was born, for about 10 million years, it was unstable. And after 10 million years, it stabilized. So the outer material was stable, inside hydrogen was burning to helium, and everything was hunky-dory, everything was in stable, comfortable environment. The sun will remain in that stable environment for about 10 billion years. We are about halfway through its life. Okay? By the time it is 8 or 9 billion years, this lack of stability in our core will start showing, and for another 100 million years or so, we will be burning sun will burn helium. Then for another billion years or so, it will burn carbon, calcium, etc. By the time it comes to calcium, which is close to iron, it's a question of few days to few hours to few minutes. The last silicon burning cycle, in fact, lasts less than a minute. So, and the star then goes into an explosion. The explosion itself will be, well, the explosion itself is a matter of few seconds because light travel time is that kind. Its core effect, so essentially that object will remain opaque to what is happening inside for about 100 days. And after 100 days, you will be able to see the innermost core of that explosion region that is happening. And that outer dispersal can remain alive or visible for hundreds of million years. Yes. Do we have multiple black holes in the galaxy? We have the closest black hole to us is about 5,000 light years from us. My my back of the envelope guess is that there must be about 1,000 black holes in our own galaxy, but nothing on the size scale of what the central one is. These black holes that we see typically are about 5 to 10 times the size of the sun. So they are small black holes by astronomical standards. And then typically you would expect a few thousand. Every 50, if you assume that a supernova explosion happens once every 50 years per galaxy, essentially every galaxy is producing a new black hole every 50 years. And you can multiply by the age of the universe and you know how many black holes will be there.
Is there any concept of multiple universes?
Is there any concept of multiple universes? There are 2 or 3 ways of looking at that question. The first question to ask is that we have a certain electric charge that has a certain value, proton charge that has a certain value, the gravitational constant has a certain value and so on. And you can ask me a question as to why does it have that value? And I don't know. Okay, there is no physical rule by electron charge or mass should be so much and so on. So I can always imagine another universe where the electron charge is slightly different, the proton mass is slightly different, then it will be a completely different universe. Okay? And you can argue that maybe there are other universes with this kind of universe. The problem is we will never know about those universes. There is no way of exchanging signal between those 2 universes, and the space itself is a very peculiar concept. So we will never know. So there could be multiple universes where there is no, the electron charge is different, the proton mass is different and so on. The other way of asking that question is even more tricky. What is happening, it turns out, is that when you really look at microscopy at quantum, at really nuclear level, it turns out that the events are not certain. In the sense that Einstein told us that mass and energy are equivalent. Now energy we know from our experience with light that energy has a wavelength and a frequency. Okay? So if I swing a string, for example, it has this signal that goes through which has wavelength and frequency. So if the proton has a mass, essentially it has a wavelength and frequency. So when you ask me where is the proton, I can only tell you that it is within this uncertainty limit, within this wavelength length. Okay? Now if I take 2 electrons and bang them, I am completely confused. And there are even funnier things happen where causality is really not fully obeyed. You can see funny things happening in the sense that I can make a cloud artificially in which the refractive index is such that you know what happens when we pass light through glass, the rod seems to bend because the light has a slower velocity in the glass medium in the water than in the air. And when you do that tricky things with very small objects, it turns out that even causality gets into trouble. So our question is, how did that a particular sequence of event happen? And I cannot tell you definitely that this event will follow, this event will follow, this event will follow. The universe is not deterministic. Given that universe is not deterministic, there is a probability that something else could have happened. And that I am seeing only one universe where that particular probability sequence I am seeing. There could be another Mayank Vahia who could be dead by now, there could be another Mayank Vahia who could be talking in Bombay right now. But then that universe is disconnected from me because of the fact that I can't exchange signals between them. So there are parallel universe ideas that go with parallelity of saying that universal constants may be different. There are parallelity of arguments because we don't understand quantum mechanics, and if the probability argument is correct, then other less probable events must have happened in some other universe, and that would become a parallel universe. Which means that every trillionth of a second, multiple parallel universes are being created for every piece of matter that you have in the universe. Which becomes absurd from the sheer thought of it. But theoretically, you cannot deny its existence. Big Bang theory is really real for a variety of reasons. That we have seen this, I told you, 1 meter and 10 meter and 100 meter. That data has been confirmed by several hundreds of thousands of galaxies. We have seen that. So we have one idea. Second thing is that you can ask yourself that if suppose there was a Big Bang, what next? Because all the matter was created in the universe at the same place at the same time, it would be extremely compact. It would be so compact that if any light is produced anywhere, it will be absorbed immediately. And you can do your physics and say that the universe had to be about 300,000 years old and of this size before the light could escape. And then when you go back and observe, you see that. You see that the closest that you can see to the Big Bang is when the universe is about the age that you would predict. The third thing is if I take a piece of vessel, and if I heat it and let it cool, it has a certain way of cooling. If I say the universe was born in a Big Bang, then I say that after that there was no heating and it was cooling down, what would be its average temperature? And the average temperature would be 2.7 degrees Kelvin. And when you measure the average temperature of the universe, it is 2.7 degrees Kelvin. So we have 3-4 independent pieces of evidence which suggest that Big Bang happened. Yes?
space is expanding. The further we look away, the rate of expansion is greater. So, is there a point at which the expansion is so far that light can't even reach it?
Yes. So that's why I said when the first, okay, there is a very peculiar problem to the universe. First of all, yes, light disconnected objects exist per se, where even light will never reach us. The second more interesting problem we have is that when you look at the surface of last scattering, where you would expect a last object, we were expecting great inhomogeneity, because as the universe was being born, proton would attract proton to each other, or proton would attract an electron, and there would be a little cluster of elements, then there would be some nothing in between, there would be another cluster of elements. So we were expecting a lot of clusters of elements, and therefore that would have a reflection on the last surface that we can see. And it turns out that the last surface is completely uniform. The perturbations that you see, the differences between temperatures that you see, are much less than what you were expecting. Much less by several orders of magnitude. So for some reason, the universe, when it expanded, was completely homogeneous. And the only way you can imagine that happening, as far as our imagination can tell us, is that when the universe was born, between the 10 raised to minus 35 seconds after it was born to 10 raised to minus 42 seconds after it was born, okay, and the time scales are that small, it seems to have suddenly popped up at an unbelievable rate which violates relativity. But relativity can be violated for shorter time scales under some conditions. And so that is called an inflation phase. The universe suddenly went through an inflation. And that inflation gives us the inhomogeneity. But this inflation you can never see. So at inflation time, when things expanded so fast, those objects are forever disconnected from us, because not even light will reach from us. So there are objects that are beyond our light. So when I said the largest picture that I can show you, the universe is about 30% bigger than that.
How did we make the estimate of 30%?
We calculate, okay, we essentially estimate the inflation rate. And given the inflation rate, how much and average distribution of matter, how much matter would be now beyond my velocity? And that tells me that about 30% went so fast that I would see. For that 30%, there is a local universe that they can see, but they can't see. The next point is that there is no edge to the universe. It is not that at some stage you will reach an edge. It is like sitting on a balloon. Okay, a balloon has every point on the balloon has another point which is diametrically opposite, but there is no edge. Okay, so more or less the universe is like a balloon. A slightly more complicated picture, but an approximate picture is like a balloon, where everybody has something else that is 13.7 billion light years away, and a little beyond, but there is no edge to the universe.
Any more questions? Thank you, ma'am, for this fantastic talk, and I hope we can have such conversations in the future.
Oh, anytime.
I think we